Hello everyone, this is week 10. This week we will be talking about the frequency domain methods in control system design. Um, Last week we looked at the systems with delay and then we had some control signal discussion. So you can see that the time domain design part is practically covered, and we looked at some nonlinearities, control input signals, and some delays. Now what we're interested in is the following. We will change our perspective. We will leave the whole polynomial work behind, and we are going to use the frequency domain methods and perspective to analyze and synthesize systems and controllers. Now, what is the frequency domain? Well, actually, since we're using already the Laplace representation of systems, of dynamic systems, namely the transfer functions, we're already almost in the frequency domain. But uh, most of the time when frequency domain is mentioned, the Laplace transform or the Fourier transform comes to mind, and that's exactly what we're going to do actually here. We will use a specific substitution which converts the Laplace transformation into sort of the Fourier transformation. And in the Fourier world, of course, everything is in terms of frequency. That's the reason why we call it the frequency domain. And our approach is again going to be the following. We will have the time domain. We will have some controller synthesis requirements. We will then transition into the frequency domain, solve our problem there, and then come back to the time domain. So let's start off with a third order transfer function that we have. Let's try to calculate the stability interval for a p-type controller using the body graph. Now, since the body graph is mentioned, what is the body graph or body plot? Let me talk about that. Now, when we have a transfer function like this, all that we do is, let me, by the way, define sims s, and I have already my sim to tf or tf to sim, which I've coded myself, but you can do also on your own, which are basically just functions that convert symbolic fractions into basically transfer function or vice versa. Now let's get the representation here, tf to sim. Let's pass in our transfer function. So all that we do when we are transferring or transitioning from the Laplace domain into the Fourier domain is we are going to need a frequency here, which is going to be real by definition, and we will do the s equals j omega substitution. Now, before I move on, let me just pop up a window here. Laplace transform versus maybe Fourier, if there's such a thing that we can easily see. Or I'm just going to show them side by side. So is there something here? Yeah, nah. Well, let's just look at this example. I've just Googled it randomly. The Laplace transform, you can see x times e to the power of minus st dt from minus infinity to infinity. But if we look at the Fourier transform, we have x to the dt. So let me just show you e to the power of minus j omega t dt. So you can see basically the only difference here is that s equals j omega. This means that we are basically using a very special version of the Laplace transform, and we call it the Fourier transform. You can see the reason because it is kind of the projection at s equals minus j omega. This is a special version where we have sigma equals 0 in the S domain. And if you think about the S domain, if sigma is 0, we have no real part. We are on the j omega axis. So when we are analyzing systems at the j omega axis, we're talking about the Fourier transform. So, and in a more general way, when we have any complex region defined, if we have a certain sigma value, then we're talking about the whole picture, which is the Laplace transform. So there's a similarity between them. The way of thinking, the perspective, everything resembles the Fourier transform. So what we're going to do most of the time is we're going to substitute GSS instead of S, 1i times omega. Why? Because of the transitioning and the relation between those two transforms. Both of them are frequency domain transforms, but the Fourier one is the more engineering used one, and the Laplace transform is also widely used in engineering. But when you talk about frequency, Fourier pops up. So yeah, all that it is basically we have a certain g omega here. So let me run this, and you'll see that's it. Now, of course, when we substitute a complex variable into the transfer function, which is just a division of polynomials, what we get is we get a complex valued function depending on omega. And if we look at it like this, we are looking at it in the Cartesian coordinates. And that's not really common because of the fact that we cannot really see what it looks like or what it even means. So what we like to use is we like to transition from the Cartesian coordinates into polar coordinates. If you're in the polar coordinates, stuff becomes clearer. For example, we can talk about gain and phase, or magnitude and phase, which is quite important because it has more physical meaning than having this ratio of complex numbers depending on omega. So what we can do is we can just take the absolute value here. And we can also use the angle here. Of course, when I do this, we will see some interesting stuff here, which still has no meaning when we don't plug in omega. But when we define the body plot, actually these two things are plotted and aligned on the x-axis by omega, and that's basically it. So we have x-axis omega, which is the common axis, and then we have the top plot, which is about the absolute value or the gain of the fraction or system or the expression itself, and then we're looking at the angle in the next one, basically. So there are two plots on top of each other. The top one is the gain plot, and we have the phase plot or the angle plot, the absolute value plot, and they're aligned with omega. Why? Because if we substitute a certain omega value into this, we will get the absolute value and the angle, and that will correspond to a certain omega value. When we change omega, we still have these two data here. So what we're trying to do is basically, instead of looking at this directly, let's call it g omega val, substitute g omega instead of omega, for example, 1. If we have that, let's just uncomment this and call it omega val. Let's see. Now that's basically it. Of course, what I need to do is I need to convert it into double so that this becomes numerical data, not symbolic. And let's do that. Let's run it again. There we go. Now, is there something called angle D? I'm not sure. Let me try it out and see. No, there's not. Okay. So times 180, because it's in radians, divided by pi should be basically the value that we are looking for. So there we go. Now this gives us an idea. And the idea is the following. If we apply sine omega t to our transfer function, since we are dealing with linear time invariant transfer functions, we get a sinusoidal wave as the output here. So the output will resemble sine. It will have some different it will have a different gain, it will have a different phase, but if you know the frequency domain signal systems, or other lectures may also have taught you that the frequency only changes when the source changes, or the frequency of the source changes. So when you have omega t, if it's a linear time invariant system, it will still be omega t. But the gain and the phase will change. That's the reason why we use the absolute and angle here, or the body plot, because it shows us the gain and the phase versus frequency. So what we really look at is basically we have g omega, the absolute value, plus the argument of g omega. That's what's happening here. If you have a sine wave, if you apply it to a system, to a LTI system, transfer function, then the output will be shaped by the transfer function, by its absolute value at that frequency, and its phase value at that frequency. And if you have a more complex signal, then the Euler identity can help you out there, or the whole point of the frequency domain analysis using Fourier comes into discussion, and you can see that each or almost all signals can be represented in terms of combinations of sinusoidal signals. So then what you can do is you can just combine the frequencies and see that the transfer function will shape the output here. Since the input will be in terms of sine waves, the output will be also in terms of sine waves. For each frequency, it will have gain phase. You can then go ahead and calculate your output basically. Or you can comment on your system's behavior when you examine the phase and gain plot versus frequency, so you can kind of get the feeling what will happen when we have low frequencies, mid-range frequencies, and high frequencies, how your system will behave. Up to this point, most of the time, we have looked at step type inputs, maybe ramp inputs to a certain degree, but those are kind of slow signals, but it's not quite correct to call them low frequency signals, because the sharp edge of the rising edge or falling edge of a step input has some high frequency components in it. But in the industry, when we are designing PID controllers, we are most of the time concerned with low frequency sort of range for certain aspects and high frequency for noise and stuff like that, because, well, that's the nature of things. If you're in a car, if you're accelerating, then the frequency that you're interested in is the low frequency range for tracking. But if you have some other stuff, if you have some road disturbance, some aerodynamic forces, etc., those will have their own frequencies. Then you're trying to come up with the best setup that will reject the disturbances and attenuate the noises in some certain frequency ranges, but then tries to track the whole input in some frequencies, probably low frequencies. So therefore, we have this body plot, which gives us the absolute value and the phase, so the gain and phase. So I can, for example, conclude that if I have sine t, it will be rejected or attenuated to a higher degree, because we see that the gain, corresponding gain, is quite low. And yeah, and then if we go on with that, we will see what happens to what frequency. So what we can do is we can just have an omega vector here and have, for example, 0.1 with 0.1 increments up to 0. Let's say 3. We start simple. What we can do is we can open up a for loop, omega vec, and then have this whole thing here. Since we have an omega vector, since we will have multiple gains and phases and we want to plot them, what we can do is we can do gain equals zeros and then the size of omega vec. So we're kind of generating a same-sized vector here. So when we calculate this, I'm just going to save it into the ith value here. And I'm going to do the same for phase. There we go. Of course, this will be omega vec I. So let's run this. And again, now we have gain, phase, and omega vec. Now, since we have these values, and I'm going to update the interval of omega vec, I can just go ahead and plot the gain plot, the phase plot, and see, and basically generate the body plot myself. So let's have a subplot, 2 rows, 1 column. The first one of that is going to have X label omega because that's frequency. Y label is going to be basically G omega. What else do we have? Hold on that stuff. Hold on, grid on. Yeah, X1 equals GCA. This is of course a text. There we go. Now this will be argument of G omega. Call it X2. This is the second one. And that should be it for now. So what we can do is we can plot on top of AX1, omega vec, gain, maybe a certain color, and a line width. AX2, the phase, and there we go. So let's see. That's the result. Of course, since we have only 3 frequency values in our vector, this doesn't resemble a body plot, but let's increase it up to maybe 10. It will take some time. Now, since we are most of the time interested in low frequencies, mid-range, and high frequencies on a single plot, what we do is we basically just create logarithmically spaced omega vectors because, well, if you use linear spacing and you want to check out 10 to the power of minus 3 and then have basically also the step like that, and then you're checking for this, the whole length of this is too much. If we define it like that, the length of that is a bit too much, as you can see. In order to limit this, what we can do is, we're not really interested in everything because that will also not fit here. We will use log space to logarithmically space stuff. So we can just tell it to use 10 to the power of minus 2 and 10 to the power of 2 with 100 sample points so that we have a higher performance in calculating these values. There we go. Now this still doesn't look like a body plot, like a conventional body plot. And the reason for that is that on the x-axis you can see we have linear spacing. It's just spacing it linearly. Actually, we don't have linear points, but it is displaying it like that. So what we can do is we can just say set, and then this is kind of a little hack maybe, x scale. So we're setting the x scale to log. We're going to do that for both of them. And that's basically omega. The x-axis scale is going to be logarithmic, not linear. And the x-axis is omega vec itself, not the y-axis, not the y scale here, the x scale here. So here we have a more body-like plot that we like to use here. Now there's an issue here, and the reason for that is the A10. It's a periodic one, and it has some asymptotes, and it has a jump here. I don't recall it now, but I can. I did remember it to fix. But do I remember it? Well, let me try it out. It's okay if you cannot fix this because we will not use this at all. But just to prove my point, let me try to fix it. Now, the phase values here, they jump from a certain value. So if you look at it, you can see it goes on negative. When you hit 180 degrees, you see that it kind of jumps to 180, from negative 180 to 180. whereas this should go continuous. But since there's an asymptote at 180 and negative 180, there's a misalignment going on here. So what happens if I... well, let's see. By the way, you can use A10 2D and get the real part, imaginary part. You don't really have to use apps and angle here, but those are the functions, so I didn't bother. But this is actually the real part squared, so maybe we should do that. Part squared plus imaginary part squared, and then the square root of that. So that is what it is, actually. And you can use A10, but I don't recommend it. So A10-2 is a better way of doing it, because A10 is only in the first quadrant. It says that here it is going to be in radians, except for real complex inputs, returns values in the interval minus pi divided by 2 and pi divided by 2. It's not the whole spectrum. So instead of using that, you can use A10-2, which returns a 4 quadrants arctangents of the input y divided by x. So A10-2 needs the imaginary part first, and then the real part second. And we don't really have to do this conversion here, because we can use A10-2D, which returns us the same thing in degrees. So, but the problem here is that we have minus 180 degrees, and then it will jump. Let me just run it again with the updated version here and see what the phase vector looks like. And again, we have the same thing here. Nothing to change. That's the same plot, but we have a jump. Now, what would happen if I add 180 degrees? This will become 180. This will become 0. Then we will 360. Yeah, I'm directly going to try it out. I need to think about it, but I did forget it. So there's something, we should do something along these lines, where we take the mod operation of this for 360 or something like that, and then substitute maybe 180. I did not write it down for some reason, I don't know. Don't subtract anything. Let's try this out first. That was a quick way of doing it, but yeah. It starts with 180 and goes on like that. Maybe we should add 180 to it, and then mod it, and then 180 it again. Yeah, it didn't work like that. Seems to be working, but I didn't see if it was correct or not. So let me just try once more. The shape is there, but we need to shift it basically by 360, I guess, because it should start negative. That much I know. So let's see, did we shift it right? There we go. Now this is just MATLAB specific, or A10-2D specific. You have to get rid of the, you have to take into account that there are asymptotes, and you should just shift or take that that jumping, bring it down. That's something that is MATLAB specific at the point here. But yeah, nonetheless, we've just managed to convert it into a proper one. It doesn't change that much, because yeah, it is just a realignment code. So you can use that too. Or you can just skip this whole thing here and use the body function on its own. I just wanted to show you that this is basically it. So I'm going to show you how to use the body function on its own. You can see that this is not decibels. You can just take 20 log 10 and then plot gain. Then you will get the proper body plot result here. Before I go on with that, I can see that there's a certain gain, 0.04, and then it drops down to 0. So this kind of rejects all the signals when you apply it. when you apply a sine wave to it. Now, I could actually do something like along those lines, like let's have a 2 by 2 here, and I guess it was 1 and 3. Is that possible? Whereas this, actually, we need 1 here and 3 here, and 2 and 4 maybe should be a grid on its own. So there was something like this as far as I remember. And I'm just going to plot the step response here, hopefully. So let me just run it like this to first check if I positioned it correct. So you can see I can stack the body plot with another axis here. Here you give some indices, then it will just take them individually, but you can give it an array so that it will stretch to that. So, and what I'm going to do is I'm just going to use a certain signal sine 2 times pi times t. I need a certain t value here, 0.01 up to 10 seconds maybe. I don't know. And I will use, so y equals LSIM, linear simulation. It needs the transfer function. It needs the time and input, or input and time. So if you don't remember, like me, you can just look for LSIM. System input time. Okay. System input and time. Now then we are going to plot this ax3 t comma y, maybe k, and then also line width 2 here. There we go. Yeah. Let's see. There we go. We have this kind of thing. Now let me also maybe plot the input that I've generated here and my output like this to distinguish them. And you can see basically it rejected the input at this certain frequency that I've used here. So it was basically omega equals 1. That's exactly here. And you can see, well, it's going to go to 0. Now, of course, if the system had a higher gain, everything would change. Let me just show you. So now we see that if we, for example, have 10 to the power of -2, which I'm going to test in a moment, it would basically just get passed through the system, or the output would not be attenuated. If this is a filter, for example, these frequencies pass through the filter, but these frequencies are rejected. So let us try that out. When we have 10 to the power of -2 or 10 to the power of -1, so 0.1, I'm going to multiply with omega val, and this omega val should be 0.1. In fact, what I can do is for omega val, I would assume that the time one should be enough. Yeah, let's do it like that. We have different inputs for omega val in a vector of 0.1 and maybe 10. We're going to do this, simulate that, and have that. So if I don't provide it a color, maybe it will be even better. Maybe we should also have legend show and maybe location best. And here we should maybe assign display name. and then have the frequency here. So omega, maybe something around this, U, and then num to str, omega val, and then something like that. So this should probably work. And here, yeah, let's try it out. Of course, since we've changed the frequency, we kind of messed it up a little bit. But you can see that for the low frequency, why is it red? Because we give it a red color. Yeah, that's the problem. Let's don't give it a color. Let's zoom in a little bit more. So now we can see that the low frequency here kind of is passed through. When I zoom in a little bit, I couldn't. Let me take the zoom tool here. Come on. So there we go. If I zoom in a little bit, we can hopefully see, but not really. But we can see that there's a signal hidden here. Maybe I should just, yeah. Let's not bother with that. We can see that the one frequency, which is obviously the low frequency, 0.1, we can see it is not that much attenuated. But if it's a high frequency one, it is rejected basically. You can see that it's around 0 here. And why is that the case? Because here we have a drop of gain a little bit and a little bit of phase, but it's mostly resembling the original input. But here, since we have 10 as the frequency here, you can see it has a very low value and it is basically rejected. Now, let's actually get rid of this whole plotting stuff here. And let's get rid of this. Let's have the body plot on its own. There we go. We fixed it basically. Now let's convert this into the body itself. And you can provide a certain omega vector here, but we can all skip this whole thing here. And let me just get rid of that, get rid of this, also get rid of that. We don't really need anything if we are trying to solve it. So I'm calling it magnitude phase omega. You can call body and then have GS. And the only thing that we should do then is to call something called squeeze here. Squeeze. And all it does, it gets rid of the extra dimensions here, basically. Because we will have extra dimensions, since it could be a MIMO system, then we would have multiple input and outputs. There would be channels, and we would have body graphs from input 1 to all the outputs, from input to all the outputs, etc. So there would be a matrix structure. But here we are concerned with LTI systems, so what we can do is we can just get rid of the extra dimensions in phase and magnitude if there are. We're not really interested in them. So since we've called it, yeah, let's call it magnitude now. So that's the convention, so I'm sticking with that. There we go. Nothing should change really. We should end up in the same plot here if we don't have omega vec, of course. So now it's called omega, so maybe we should call it omega vec. If you don't provide it any frequency range, it will pick its frequency on its own. Here you can see it picked 10 to the power of 3. Maybe I'm only interested in the log space one that I've created previously, like this one here. So I can also provide it here, omega vec. Since I did provide it, I don't need it as an output argument, and the frequency range will be updated. So it goes from 10 to the power of -2 up to 10 to the power of 2. And that's basically it. You have, again, the same plot. And you don't really have to bother with all this stuff here. I just wanted to prove that you can use the substitution s equals j omega. You will end up in the phase and magnitude. If you take the square root of the sum of real square and imaginary square, you will end up in the gain or the magnitude. If you use the A10, and we did need some shifting here, if you do that, you will get the phase, and it's nothing else but the data that is provided by the body plot here. So how can we calculate the stability here? Now that's the important part. We didn't even start to address that problem here, but let's do. Now, since we are interested in a certain closed loop, since we are talking about stability, we actually have, again, this setup here where we have a K gain and the system here, and then this feedback here. There we go. So this is basically our structure here. And we know that when we have this kind of structure, we have Ts equals K times Gs divided by 1 plus K times Gs. So that's that. Now, all that we do in order to analyze the behavior of the closed loop here or the open loop, all that we need to do is we need to transition from Laplace domain into the Fourier domain. So what we are going to do is we are going to substitute s equals j omega, basically. And if I do this, I can just call everything like this here. Now, what is stability? In terms of the body plot and the frequency domain, what we can do is we can define it like tending to infinity, for example, not being bounded. So tending to infinity is the important keyword here, because if you think about a ramp function, it will tend to infinity if t tends to infinity. But if t tends to infinity and we tend to a certain value, then it is kind of bounded in terms of stability. That's called bounded stability. If t tends to infinity and we tend to 0, then that's absolute stability or Hurwitz stability. Now, what we are going to do here is we're kind of trying to emulate the tending to infinity. So if t tends to infinity, we should see, so infinity, we should see basically that the output itself should tend to infinity. So that's it. Of course, for bounded inputs. So the input should not be infinity. If you plug in infinity, it goes to infinity. Doesn't make sense. But if you have, for example, a step input or a sinusoidal wave as an input, but it still goes to infinity, that's what we are interested in here. So if t tends to infinity and the output should tend to infinity, and if we look at this here, we basically have a fraction, nothing else. So we're talking about a fraction, and when we have a fraction, the only possibility that comes to my mind is that we should have a division by 0. If that's the case, then this would be something that we're interested in for the stability here. So this would tend to infinity. Even though we have something constant here, we should have a division by 0. And since this is the denominator, if the denominator for some reason becomes 0, then we would have a division by 0. So instability occurs if we have a division by 0. That's our assumption here. And yeah, we will investigate the conditions for this, when it will happen, because then no matter what the input is, the transfer function will just tend to infinity. And we're interested in sinusoidal waves here, so that's basically it. What we are going to do is we first of all need to remember the fact that g omega here is complex. So it's an element of the complex values. So if this is equal to 0, I can move this 1 to the right-hand side. It becomes -1. And at this point, I'm looking at something that will help me out here. Here, since we are not in the Cartesian coordinates, we like to use the body graph, we like to use the polar coordinates. We can state this differently. The gain of this -1 is basically 1, and I'm going to kind of use this sort of notation here. And if I have 180 degrees, then I would be talking about cosine 180 degrees plus I times sine 180 degrees. So that would be the case here. And you can see that the sine here will be 0. So, and the cosine here is -1. Therefore, it is -1. Oh, I'm using the Euler identity here. You can see this is corresponding to 1 and 180 degrees. So the gain is 1 and the phase value is 180 degrees. What you can do is you can just take the real part, which is basically -1, take the square of that, plus the imaginary part, which is 0, and then take the square root of that, which is basically 1. And the imaginary part is 0 divided by -1, a10 to the a10 to d, you would get basically 0, -1, and you get 180 degrees. So you can see it is basically 1 and 180 degrees. So this is important. We need the gain to be equal to 1 and the phase to be 180 degrees. If that's the case, this multiplication will be equal to -1, and since the denominator is 1 plus k times g omega, this will become 0. We will have a division by 0. This is all we need to know. The stability criterion, the Nyquist criteria, all depends on this. If you know what this means, then you're basically good to go. Yeah, what now? So, since we have a scalar k, what I'm going to do is, I'm assuming that k is going to be positive or negative, since it's scalar. I can convert this condition into the following. The absolute value of this should be 1, and the argument of that should be equal to 180 degrees simultaneously. So there's an AND operation here, and there we go. So this is what I'm looking at. By the way, you can also use -180 degrees because it's a periodic thing. Again, A10 to D, it's periodic. You can also use -180 degrees. Since we are concerning with control systems, most of the time 180 degrees is what we're looking for. So the absolute value should be equal to 1, and the argument or the phase should be 180 degrees. So since k is scalar, this is important. I'm going to have k positive, so k can be positive, and we will also look for the negative case. If k is positive, I can do this. So k times g omega is that, and we know that the multiplication, the argument of the multiplication can be written as the sum of the arguments of the individual terms. So there we go. Since k is positive, the argument of k is going to be 0. It's a positive value. If it would be negative, we would end up in 180 degrees or -180 degrees. But since it's positive, we get rid of that. So we have the argument of g omega here. Now we are at a certain point here. We have a argument g omega equals 180 degrees or -180 degrees. And then we have k times the absolute value of g omega should be equal to 1. Now let's let that sit here, and let's begin with the negative one here. If k is negative, So if this is negative, I will have minus k times g omega here on the left. And since the sum of these should be negative 180 degrees, and since k on its own is negative, like minus 1, we would have minus 180 degrees here. They will cancel each other out, and we're left with 0 here. So these two cases here are basically the stability bounds that we are looking at. So let me just delete everything here. The only thing that we should remember here is these two conditions here. K times g omega can be equal to 1 if the argument g omega is negative 180 degrees. Then we will end up in positive k boundaries here. If k is negative, then minus k times g omega should be equal to 1, whereas the argument of g omega is equal to 0. The nice thing about this, about the p stability and the body plot, is that we can basically use the system on its own, use the body plot of the system, look up the negative 180 degrees and 0 phase values, come up with the frequency value, so omega star, the corresponding frequency that we're interested in. Because we have two simultaneous equations or conditions, what we need to evaluate is the frequency that we're interested in. At which frequency has the system negative 180 degrees phase or 0 phase? Both of these 2 points are going to be critical points, and we're going to use that frequency, plug it in into the first condition, and look if we can satisfy them both. Since this is not depending on k, this is what we search for at the beginning, because the system does not change, the body does not change, so this condition doesn't change. If there's no such frequency, then there's no stability boundary. If there's such a frequency, then this is a candidate point that we should look up for. And if the multiplication here can also be satisfied at that frequency, for that value of k, we will have stability bound. So let's look this point up and try to come up with the stability point. So I know what the phase vector looks like. What I need to do is I need to search for the point where this becomes negative 180 degrees. Since we're using a logarithmic scale, that exact frequency may not be available here. So I'm not going to look for minus 180 degrees exactly. I'm going to look for the closest point. And the reason for that is this here. In omega vec, we have only these frequencies, nothing else. But it could be somewhere around between 9 and 10, but that exact point may not exist. Or here in phase, I can directly show that too, or phase. You can see negative 180 degrees is not there. It's between this one and this one. So therefore I will get an approximate value, therefore an approximate bound. We can improve on that later, but we will basically search for the closest point, not the exact point. Visually, you're doing basically the same. I'm going to do it programmatically. So I'm going to define a error here, and it will be the difference between the phase value, the phase vector, or negative 180 degrees. So I'm doing it in one line, but if you are interested in maybe the C-type version here, what you can do is you can just open up a for loop from I1 to length, and then the length of omega vec. For each value, we are going to assign the error here, I, the phase I value, and that's basically it. Maybe, let me just comment this out. Maybe we need to define error equals 0 size omega vec. So that could also be it. So let's run one. We missed omega vec. We misspelled it. There we go. So you can see we have an error vector here. And here somewhere it becomes the minimum value. You can see it's kind of this parabolic shape, sort of, and we're looking for the minimum here, since we're using the absolute value, and since it does exist at this point. So we're looking for the minimum value here. So value index minimum of the error here. So that's going to be value, that's going to be omega, and I can check for the magnitude and phase also to see what it is, or maybe even a display message here would be nice to inform ourselves to pick the right points here. So this is going to be the magnitude, so G. I can also generate this part, I guess, plus string, and then plus, and then back this, where we have omega index is going to be this one here. I guess we could also do this for phase. So argument of G omega. I guess we need to place this here. Yeah, that should be it. The phase index. So it is omega vec. There we go. Now you can see that at 5.5, maybe we could also append a J here to indicate that this is basically, oh, here J, to indicate that we plugged in J omega. There we go. At 5.59 radians per second, we have basically 0.07, and the closest value is 177. What we can do is, since we see what the phase vector looks like, we have some unnecessary stuff here for frequency. The frequency is around 10. It's 5.59. We could maybe decrease this portion here, or we could increase the amount of points that we have here, maybe 400 points. So let's run it again. So you see it is a closer value. Let's have even more. Here we see it's 179.96.89, close enough. The frequency is 5.82. The error value is 0.03, which we are not really interested in, but it's close enough. And we see that this is basically that. Now, if we recall this here, we can see that this is approximately met here. The argument here is at this frequency minus 179.96. The only thing remaining is that the multiplication with k and g omega should be equal to 1. We know this portion here, so we can basically come up with k that will satisfy the first condition. And we're looking for a certain k value. Therefore, the inverse of g omega will give us the exact k value that we're interested in, because the conditions are basically here. We've met the second condition. We're looking for the first one here. So, by the way, you don't need this for loop here. Let me demonstrate it to you. You can just do it the MATLAB way, because you can substitute a vector and a scalar. In MATLAB, it will do it element by element. And we get the same result here. It doesn't change. So it's a more compact way of doing it, and I like to do it. So yeah, you can maybe also insert a if val is maybe less than 1e, I don't know, maybe 1e minus 1, 0.1. So then display it. Otherwise, it would be maybe it's not available. So we're interested in only this one here. So there we go. We have basically the solution here. So the only thing that is left here is to display the k value that does this. So plus string and then 1 divided by magnitude here, magnitude index. So there we go. Let's run one. We see K is approximately 13.98. What we still can do is we can mark that point on the body plot. So let's do that too. So we have displayed it here. Let's plot this point on AX1 omega vec index and magnitude index with a red square, for example, line width 2. And we can repeat it for the second plot where we use the face here. If I could spell it right. It's called face. There we go. We also have some annotation on our plot. So we were interested in minus 180 degrees, which corresponds to this point, which is a certain frequency. We used the same frequency to read this value, take the inverse, and it gave us the value here. Of course, our original system was a more dramatic one. So let me just change it and apply it again. Now you can see it's almost 350, 349.64 seems to be an approximate bound on our p-type controller. Let's also repeat this for the negative portion here. So let's basically use the same approach here. Now we are looking for 0, so I'm going to search for 0. And once that's happening, we will have the index, everything there. The only difference being that if this is met, and we'll see if it's going to be or not, let me also throw in another empty display here. So it will move one line down. So there we go. Now, the only difference being that we're searching for 0. If that's approximately met at that frequency, we will need to have another minus sign here. So K is not going to be 1 divided by that, but it will be minus 1 divided by that. And I'm going to use blue for lower bound. So so what is the error value here? Is it not small enough? Yeah, it's not small enough. Why is that? So face looks like this. Yeah, because it's not small enough. So what we can do is we can maybe increase the frequency here or tighten, loosen the bound on this here. Maybe for this, let's call if it's less than 1. So there we go. We see that 0.01 is basically the point of interest. And you will see why, because it's basically omega 0 here. The closest value that we get to 0 for phase 0 is basically here. So it's going to be the first frequency value that is available here. So that was the reason why we should maybe update the omega vector. The bound will tighten, but we're interested in basically omega 0 here. And we see that the lower bound is minus 24. This happens at the following. We will have the argument 0.01 approximately equal to 0. That's not really 0, but yeah, we should maybe update this here. But if I touch this, the precision will go away for basically the upper bound. But yeah, let's update it. Let's go to minus 3 with 500 points. Run it again. Still not there. Interesting. Value maybe. Still 0.08. Doesn't that satisfy our condition? It does. So maybe we should run it again. Oh, now the upper bound doesn't set. Yeah, I was expecting that. So maybe comment it out and see. You can see the value is now 0.26. Now we are not hitting that part. So yeah, we need to increase the amount of points. Let's pick more points. Now it does. It's a little bit overflowing here, so it means that, yeah, we should be picking a lower value, but not really that important. Let's call it one more time. There we go. Now we can see, of course, this is 180 something, so it should be a lower value than this. This is not the exact bound here, but we can see it is between -24 and 350, seems like it. So these are the 2 points that we have used to calculate that. Again, I repeat, these two conditions, one given in line 18 with 17 and 29 and 30 are important to note because those are basically summarizing it. We're looking for the point where the phase of the system is -180 degrees. That frequency, plug in that frequency, get the gain value or magnitude, take the inverse, you are ending up with the positive bound. Look for the phase 0 here, or the closest point to that. Look at the frequency. At that same frequency, read the phase or magnitude value, the gain or magnitude value. Take the inverse, and you have also a negative sign because you're looking for a negative bound. And you have the negative bound. I've coded it so that you might change the transfer function, and it will try to look up the best point that is suitable for us, so you can use it basically as a template. So we can verify this info with another figure, maybe, and use the R locus here of GS. So let's run that. There we go. What we have to do is we have to click on basically somewhere here, 341, 350. You can see it's kind of the bound that we're looking for. Can I meet that? Yeah, 350. It still has some negative part, so 350 is kind of the bound. And for the negative one, we can also have basically the negative root locus here. Hold on, maybe we can give it a color red and blue to match the colors, maybe. So there we go. On the red one, we can get the upper bound. On the blue one, we can get basically the lower bound. And you can see the gain value 24 here, approximately. You can see this is already on the right half plane, so it's 24, but the negative sign doesn't show up in this here, but you have to append it yourself. And you can see that the upper bound is also in the range, so the blue one corresponds to the blue one, the red one corresponds to the red one. And you can see we're basically on the j omega axis, and you can also check out the frequency here. You can see 5.8 approximately is the frequency here. You can see it matches the frequency here, and it's almost 0 or exactly 0 here, the frequency 0.02. So you can see it also matches that. So the j omega crossing frequency is basically the frequency in the body plot that we're looking for, because the S domain is projected on the j omega axis if you're transitioning from root locus to body plot basically. So if you plug in S equals j omega, you're projecting yourself on top of this j omega axis. You can only move on the j omega axis if you're on the body plot, but otherwise you have more information in the root locus plot. But we're interested in j omega crossings because those points correspond to stability points, and the stability is basically modeled with division by 0 here. So that's basically the first part that we're interested in here. Calculate the stability interval. Of course, it's a quick example actually, but we didn't look at it just on the surface. We dove deep into the theoretical parts. Now the next part is going to be basically about designing a p-type controller. So, um, let's use the body graph to design a p-type controller with 10% overshoot. Now, when you look at the zeta, the damping ratio zeta, we notice something interesting here, the damping ratio zeta, and it is the following. When we look at the S domain, when zeta is equal to 0, we are basically on the j omega axis. And we, in the first part, we have actually determined zeta equals 0. Possible solutions for that. Let's go with the positive root locus here, or the positive gain for our controller. And we actually have determined 350. We know that this value will correspond to zeta equals 0. We also kind of know that for most of the systems, when we hit this bound here, we have a increasing sine wave or an exact sine wave or even a damping with the sine wave. So what we can do is we can assume that somewhere before 350 or some value less than 350 should end up in a zeta value. And this zeta value is going to be between 0 and 1 or greater than 1 or exactly 1. We don't quite know that. For second-order systems, since zeta is only defined for second-order systems, we can basically see that there should be a relation between zeta and our frequency or point where we basically pick this value. So what I'm trying to come at is the following. We are going to use the distance from this stability bound or this margin in order to match that with a certain zeta value or a certain damping ratio to the system. And then that would correspond to a certain overshoot. So when we are looking for overshoot equals 10%, this will then translate into a certain margin or distance from the face, which is minus 180 degrees here. So we are looking for a certain distance here. So the face value will be minus 180 degrees plus some distance, or a little bit to the left. And we are going to hope that that will correspond to our zeta value, which we can calculate, 0.59 something. Because we use 10% most of the time, I think that this was the value for it. Now, this should correspond to a certain face value. There are two ways of doing this. One of them is the hard way. The other one is the easy way. So first I'm going to show you the hard way of transitioning from overshoot to zeta and then to a certain distance. We call this distance phase margin because, so phi m, because this is basically the margin, the distance from minus 180 degrees. And if the zeta value is the one that's given, let's calculate that for instance. So zeta equals, as usual, minus log overshoot divided by the square root of pi squared plus log overshoot squared. So this is zeta. $59.12. So now there's a relation between phi m, which is even worse than the zeta overshoot relation. A10 2 times zeta, the whole thing divided into the square root minus 2 times zeta squared plus another square root 1 plus 4 times zeta to the power of 4. Now we can use a tan d in order to see what it is going to be in degrees. And it's 58.59. So this means the following. If this phase margin is equal to 0, then zeta is equal to 0. So if zeta is equal to 0, phase margin is equal to 0. If zeta is, for example, 0.6, roughly, then phi m, this margin becomes 58, 59, let's say 60 degrees. So that's what it is telling us. So this distance is, of course, accurate for second order transfer functions. We don't have a second order transfer function here, but we will kind of try to use this no matter what. So in the body plot, we don't really care about the order of the system because the model of the system is not really used that much. You have a body plot and then you forget about the transfer function. You just have the body plot. For that reason, on the body plot, we will search like it is a second order transfer function. And the search is going to be about this phi m, this phase margin, the distance from minus 100 degrees or minus 180 degrees or j omega axis. How far should we be away in terms of phase, in terms of phase angle? We are looking basically at that. If we are on the right spot, then we should be good to go. Now, here, what we're trying to do is we're trying to basically alter the system, change the system in such a way that the gain at which distance we are interested in is going to be 1. The multiplication is going to be 1. So basically, we pick this one here, assuming that we are interested in the positive one. And we're trying to do this, but with phi m plus the phase margin. So instead of amplifying it or making it exactly equal to 1 at the minus 180 degrees boundary, we're just shifting the phase value by this margin. If we shift it enough and accurate, then we should end up in the controller that has the overshoot that we're looking for. But the bad news is that this should hold for second order transfer functions. So this might be a little bit off when we calculate it. So I'm basically going to just calculate this phi m here. Let me delete everything here. And I'm going to search for the following. Let's call it phase desired maybe. And we're looking for minus 180 degrees plus phi m. So the desired phase value is going to be this. Let me get rid of this root locus here. And let me just copy this part here and move this one here. So there we go. We have our specifications. We get to the phase desired. So let me display. Or let's just call it phase des plus string. There we go. So the desired phase value is this. We're just notifying ourselves. And therefore, we're just going to look for phase des, the desired phase. So you can see if this is equal, then this absolute value should be equal to 0. We're looking for the minimum value or where this minimum occurs. We look at the frequency. We look at the phase value. So that was kind of easy, I guess. The stuff that we're trying to do is repetitive, so it's kind of the same thing. We look at a certain point and we take that point. But the important part here is to know where to look at, because we have a desired phase angle. We want to satisfy this with the given equation that was here. So let me just copy this one too. Let's paste it in here. The only difference being with phase margin, so phi m. So we're just shifting the angle condition a little bit, and that's basically it. We're not interested in anything else. I'm just directly picking it from here. So let me just close this figure. Let me just open this one. And you can see that's what I'm talking about. We're just going a little bit to the left. Let me just run it again for the color to take effect. There we go. This magenta point here is exactly the point of interest. And since this is the stability point, and since our gain value drops here, it means that k on its own is increasing. So it means that this is a lower value of k, because the relation between k and g omega. And what we're trying to do is, at this frequency, we're bumping this up to be equal to 1. When that's satisfied, we hope that our overshoot will be as we wish it should be. So you can see the frequency is lower, and the desired phase angle was this one here, and we got this point here. So let's see what happens if we take k. So we've practically designed a p-type controller by just looking at the body graph and calculating the relation between overshoot, zeta, and phase margin. Using the phase margin, we just skipped it a little bit to the left, and we took the magnitude here, inversed it, and that's basically it. So let's see what happens if we really do this. So let's have TS, feedback, and then maybe we should assign k-val now. Or just skip k-val, I'm not really interested in it. This times ts, 1. Info is going to be step info. TS. And let's display overshoot is, and then string info dot overshoot percent where it should be string OS percent. There we go. Now let's run it. So it should be 100 times this, because of the way of our definition. So there we go. Now we can see that the overshoot here is 26.5% instead of being 10%, which was our aim. And here, again, the reason is because we basically have a third order system. So if this system is a third order system, if it has some delay in it, if it has some other stuff that is not really modeled with using zeta and omega n, because if you remember, zeta and omega n is just a way of defining a second order transfer function without a zero, just an all pole transfer function, then these differences are expected. But the nice thing about body plots and the fact that we are kind of using this distance with a proportion to overshoot or zeta is that we can tune it a little bit. It seems like we need to go a little bit back, or just use a smaller k value in order to improve this overshoot. Because I assume that if I go to the right on the body plot, it doesn't matter if I'm going to the right on the magnitude plot or phase plot, I know that the overshoot will increase up to 100% because 100% overshoot is j omega axis, is the j omega axis itself. So I drop down here to 26%. So if I go a little bit to the left, so if I increase the phase margin a little bit for this system specifically, I can tune it maybe to get to a point where this hits 10%. So I'm readjusting it. So this can be used for initial guesses, and then you can just go ahead and adjust your guess a little bit more. So instead of doing this, for example, I might add 10 degrees to it to see what the effect is going to be. So did we mess it up a little bit? So phase test is 111. I guess the error value or the value here is 0.11, where we have a stricter thing here. Okay. Maybe I'm just removing this. I'm just going to remove this check here for this specifically to not bother with that. But yeah, loosening the bound is also an option, but I'm just not going to do that. Here we can see it dropped down a little bit, but we're still not there. We should maybe decrease it a little bit more. So adding maybe 20 to it. So you can also maybe assume that like this. You should maybe add it here. Makes more sense. A greater phase margin. 16%, maybe 30 will fix it. 13%. Let's make it 34, something around those lines. 12, oh, it seems like 40 is going to do it. Yeah, time point 53. We can still adjust it a little bit more. 10.02 is quite nice. So the phase margin that we've used is 100 degrees, whereas it was roughly 58 something. So yeah, we needed more phase margin than we got here. But picking this point should result in 10% overshoot because step info says so. So you can also plot the step response here, but yeah, not really that interested in it. Let's see if the valve hits. Oh, it hits, so maybe we can open it up back. Since we are only interested in the overshoot value, this should suffice. So let's see. There we go. So that's basically our solution here. And if we look at the closed loop here, we can see that due to the third order system, we have the second order part. Maybe if this pole didn't exist, this would give us a solution at phi m, but we needed to shift it a little bit due to the third order system here. So what is the roots of 1, 3.338, 8.425? So it's basically this here. And yeah, what happens if we look at the answer of one of them? We get 290. So if I divide this into our answer here, I get 0.57. So you can see that this kind of corresponds to the zeta value that we're looking for, and since the pole is far away, it's kind of dominant here. You can see this is 1 point something, 1.5, 1.6, 1.6 and 7, so there's almost enough dominance factor here, and you can see that the zeta value is the dominant part here. But this is the third order system, and we kind of ended up in this here by tuning the phase margin. Again, you can do this. You can just use this as an initial point. If it's hitting the target, it's nice. You can use that point. But sometimes we need to adjust it a little bit. Now, in terms of exams, when you're asked to do something like this in an exam, just do it once. Don't improve on it if it's not needed. Or you might ask for it if you need to improve it or not. Because if there's nothing clear, most of the time the initial solution is needed here. Because you don't have MATLAB in exams, you cannot check if it's the valid one or not. So you just need to use a phase margin without 40 and be happy with it. If, for example, you can look for time domain verification, you can then maybe conclude somehow that it will not function well, or it will based on the pole zero map of this. So let's maybe repeat this. So you can see that we have TS. Now let's run this one here. Then look for the roots of 2.563 and 12.37. So the abs value of one of the roots is this one here. So 1.2815 divided by the answer here gives us 0.3644. You can see that ideally this should be a second order transfer function, and this zeta value should be the exact zeta value that we're after. Here it's of course not really easy to decompose it into the second order part and a first order part, but maybe you can use the algebraic method and a little bit of calculation with the exact given things here, because you know what your controller is. You can come up with the omega n value, zeta value, and check if it's true or not and why it is working or not. So there is, since we know the time domain version of it, we can just see if it's going to work or not, basically. Yeah, and since I'm at it, let me talk about the fact that the body plot doesn't really care about the transfer function, about the zeros, about the poles, about dominant pole placement, etc. It has its own theory and its viewpoint. The frequency domain has its own rules, basically. And you can see that it's quite tunable. The disadvantage here, the bad thing about frequency methods is that we are not really relying on the transfer function that much. We are kind of using the body plot or Nyquist plots, etc., all the frequency domain methods on their own. And as you will see in the upcoming parts, it doesn't really matter what the body plot is, or where the body plot is acquired from, what kind of transfer function or system it is from. It doesn't really matter. The rules stay the same. You look for basically the same stuff. So yeah, it's a nice tool because you can apply it to wide range of variety of systems. But then again, it doesn't really give you the best tools here. Because for this example, you're designing a p-type controller, and you know all this time domain stuff about the p-type controller. You know that the higher the degree of the system, the difficult it becomes to push all the poles away in order to get the zeta and omega n value for the given settling time and overshoot, etc. But here in the body plot, you just have gain and phase, and you're looking for a specific phase. You use the distance, and you end up in the p-type controller. Whether it works, why it works, it doesn't really matter. You just get the result, basically. It works, but it has its pros and cons. To not know or care about the transfer function that much can be an advantage or disadvantage. At this point, it seems like you know that this is an LTI system. You know the order of the system. Why not use the time domain representation? So if you know the model well, if you're sure that your transfer function represents your system very well, you should opt for the time domain methods. And if you want to have precision, you should opt for the time domain methods. If you have a tough system, or if your system is not represented well, then maybe the body plot is quite important, because we will see there are some systems, and we will apply stuff as it is based on the body plot rules, or body rules, and nothing else. So this is basically the p-type controller design part. There's an easy way to estimate phi m, and that would be just 100 times zeta. It works for certain zeta values. And let me just calculate this one, for example, first. You see it's 58.5. What happens if we use 100 times zeta? It's 59.11. So it kind of works if you use 100 times zeta. But there's also, again, a certain assumption about that. You should have that in your lecture notes. I don't really remember that, but it should be working, basically. So there we go. We've calculated that, but I think we again hit this part here. So let's make it maybe 2 here. Now it works. 9.99, and this point is exactly the point that we're looking for. For the stability parts, we have looked at these equations. For the design part, the synthesis of a p-type controller and p-type controller only, we've just adjusted the phase condition. We've altered it a little bit. We add just a phase margin, which we can calculate from A10 formula, which uses zeta, or we can use 100 times zeta as an approximation. And sometimes if we are on MATLAB, we need to adjust it a little bit so that we match the overshoot here. So it's quite easy to design a controller using body plot, because I'm just copying and pasting and adjusting stuff about it, and that's basically it. So now let's add a phase lag controller to design to the design obtained in B. So we are going to use the p-type controller here and add a phase lag controller on top of that. That reduces the steady state error by 10-fold using the body plot. So this is basically just for the exemplification of phase lag design. And the phase lag design is actually quite algorithmic, I'd say. And the reason for that is the following. You have some steps to carry out, and that's basically it. It's for most of the body plot or body methods here. You can see that there's a certain algorithm. Search for this, get the frequency. At that frequency, read the gain value. Take the inverse. Take the inverse with a negative sign. If you're designing a controller, add the phase margin, search for that phase, look at the frequency, at that frequency get the gain, take the inverse. So it's kind of quite algorithmic. And the same goes for the lag controller. But before the lag controller, what we have to do or take into account is the gain of the system, because we have a condition that is about the steady state error of the system. And it seems like it's just the steady state error, so you can use the position coefficient in order to come up with that. So let's see. Now, we first need the steady state error here. And yeah, let me just get rid of this one too, so it stays the same. So what is our K value? Our K value is 40. We have TS. So what we can do is we can maybe get Y and T and step TS maybe. Did we have a figure? Yep. So let's maybe do again this trick here to add a step plot here. So 2 by 2. This is going to be 3. But here I'm going to use 2 and 4 to stretch that. The X label is going to be T. Y label is going to be YT. This is x3. We don't need to set the x scale to log. And we're good to go. Now, yeah. This is 2 by 2, of course. So here what we can do is we can just plot the step response here. T, y. Doesn't mess up anything, I guess not. Let's have black. Line width 2. And that's basically it. While I'm at it, let's get the steady state value, the end value here, and then so YSS is basically YSS. There we go. Now let's run this. So it's 0.62. We have to calculate basically the steady state error, which is ESS, one minus, because that's basically our input. Save that. Run it again. There we go. It is 0.37968. So what we need to do is basically we need to reduce it by tenfold. Now, let's assume that our lag controller, so we are trying to do the following. We have the reference input, the summation point. Now, we did have the p-type controller, but now we are adding a controller on top of the p-type controller that we had, and try to design a lag controller. And we are actually trying to change the gain of the controller. Now, why am I saying that we are trying to change the gain of the controller? Basically, this gain results in this steady state error. If we increase the gain, this will drop down because of the, you can just use k times gs divided by 1 plus k times cs here. 1 plus k times cs. And if you plug in s equals 0 for using the final value theorem, you can just look for the gain of the system here, which is 24. So if you apply step to gs, you will end up in 1 divided by 24. So, and this was also on the body plot, as you might remember here, 0.0417. That's basically the DC gain of your system. At steady state, your system vanishes and you have just a gain that is this one here, or 1 divided by 24. So when you are looking at the steady state error, what you try to do is, or when you're looking for YSS, YSS is going to be basically this divided k times GSS divided by 1 plus k times GSS. And if this is a value of 24, divided by 24, and if you plug it in here, you can see that the ratio here goes like this, 24 plus k, and this is YSS basically. Now, if k increases, then you can see that this will tend to 1. If, for example, limit k tends to infinity, this limit will go to 1. But that's not possible with finite values. Therefore, if k is huge enough, then 24 will lose its importance and it will be almost 1. We can try that out. We have 1000 divided by 1000 plus 24. it's basically 0.97. But if you decrease that to 100, you'll see 24 will become more significant, then this will drop down. If you have 10, it will drop down even more. This is the steady state value. So there's this high gain theorem. When you are trying to design a p-type controller, you're kind of trying to increase the magnitude of your controller. You are trying to use a higher gain value. So that's what we're trying to do. And if you know that we are trying to increase the gain value, at the end, you can just check if your design is correct or not. Because for this error value to drop down tenfold, we need to have a much higher value than 40. If you do your stuff and your DC gain of the whole controller, Fs times K, is larger than 40, you're on the right track probably. So now if this is basically the steady state value that we're looking at, and if this should have a gain, we know that this is 40, by the way. So basically the overall gain that we should end up in should be the following. Now we know what this is. This is ESS. So let me define it like that. So let me use ESS here. Therefore, for the new condition, lag controller, we should have ESS2, which should be ESS divided by 10, because tenfold. Then YSS2, for the new setup, we should have 1 minus ESS2 here. So what is YSS2? Let's see. Let me comment this out. So YSS2 should be 0.9620. If this is YSS, basically, then we kind of can solve this now. So 20K is equal to YSS2 times this one here. I'm just using the direct relation here. I don't want to use any symbolic expression here. You can do that. Feel free to do that. But I'm just skipping that part. So 24 times YSS2. Drop that, add that. There we go. Let's group K together. So that's minus. And in the K parentheses, it's just 1 minus YSS2 equals 24 times YSS2. So we have to divide into that. So let's call this K2. Let's calculate this. What's K2? 600. Now we've seen that the system on its own using a p-type controller is not even stable at this point. You need such a high gain value to get a tenfold decrease for your steady state error, but your system is not even stable. That's the reason why we're trying to use a lag controller. We have certain dynamic behaviors that we want to save, but we want to change the steady state of the system. The lag controller should not touch the transients, but should change the steady state. So that's what we are after here. Now, since this is the overall gain of our system, we didn't include this. This is going to be the gain of Fs times K. So keep that in mind. So this is the overall gain that we need here. And it's 600. So yeah, let's see. Now, what we're trying to do is we're trying to, or what we need to do is now is to update our body plot. And the reason for that is the following. We have the lag controller. Let's define the lag controller. That is tau times s plus 1 divided by alpha times tau times s plus 1. And the reason for that is this has DC gain 1. So this has no DC gain at all. I can add this K2 to this, or I can just update this whole structure here and say that I include K to our system here. I include the whole K value to our system. So this is going to be my new system here. But I'm going to add this F lag part back in, which has DC gain 1. So I'm updating my transfer function, open loop transfer function, because I have already a p-type controller. So you can basically do this like K2 divided by 40 times 40, because this part here was already designed, but our whole system gain should be equal to K2 times GS, or K2 divided by 24. So basically I'm just skipping that part and I say that, okay, now I have included everything into K2. The gain of the system should be K2. We need a higher gain than 40. Basically what I'm trying to say is K2 divided by 40 will be the gain of the lag controller, whereas the p-type controller is 40. So their multiplication is still K2. Now I need to look at the gain plot or phase plot of this, because this is basically a new design problem. So this is a new system. But luckily, and also maybe unluckily, the body plot does not change that much. Since the gain is only affected here, k is just a scalar. So what you can do is you can just use this body plot here, but you have to take into account, if you read something from the body plot, you have to multiply it by k2. If you're looking something, if you're searching for something on the plot, you should first divide by k2 and then search on GS. So in the exam, sometimes this question might pop up and you might have only the body plot of GS. So you have to calculate or just predict your own gain plot or update the values of your gain plot and read from just one body plot throughout the whole question. So be aware of that. That is something that sometimes the exam questions have. So yeah, now we're looking for basically the lag controller. We know that our lag controller has no DC gain, and we will add this DC gain at the end. So this is our lag controller. What are we going to do? Well, our strategy doesn't change that much. We can start with this part here. We have a certain overshoot, certain phase margin. Let me drop down this one here. Now we still added some portion here, but since the equation here will change, because let me just get this part here. Remember this equation here? Now this is not the case anymore, because we have something that is dynamic. So this is going to be f omega times g omega. The argument still does work like this, f omega times g omega. Actually f omega plus g omega. So we're kind of looking at this. And yeah, we know that we can use the gains here. So that can be used like this. And for the definition here, by including the gain into the body plot, by shifting it to here, I can just get rid of this. So that's the reason why I try to do something like K2 times GS here, because F omega is going to be K2, and I'm going to get rid of it. So let me just pop that out. So this is basically equal to K2, or 600 basically, and I'm going to look at 600 times g omega, so that I don't care about this part here. So I'm just writing it down roughly, 600. So here, in order to be able to look up a certain frequency from the phase plot, I need an assumption. And again, my assumption is the following, that this argument is going to be less than or equal to 10 degrees. This is an assumption since this is a lag controller, this wouldn't work for lead controller because the lag controller should not contribute any angle to the system ideally. Of course, in reality, there is a certain degree that is going to be added to the system or subtracted from the system. But I need to tolerate that. In order to do that, what we are going to do is we're going to add 10 here. So plus 10, something like that, plus 5, plus 10, and get rid of this. So there's an approximation here. If you have a scalar like the p-type controller, it's easy to do some assumptions because it can be positive, negative, it's a scalar. If you have a dynamic controller, stuff in the frequency domain becomes a little bit harder. But for the lag controller, because the lag controller is a special one, you can have some assumptions. For example, the gain should be equal to 1. You can embed the gain into the body diagram, so the gain condition is like this. But for the phase condition that you are going to do here is that you just add 10 to it so that if that's the case, argument f omega plus this, so I'm just adding argument f omega. If this is minus 8, minus 10, then the effect will vanish and you will end up in minus 180 degrees plus phi m. So that's the reason why we have this assumption. It should be less than or equal to, at least, so that we don't hit the stability bound. We're just being safe by adding 10 degrees. It could be 5, then you're just a little bit safer, but that's no issue. It's kind of an iteration. You can also iterate and try to tune it a little bit more here. But let's first solve it and then see what I mean by that. So basically, therefore, I'm just increasing it by even more, like 10. So now I'm really off of my initial phi m, but that's no problem. Now we look at a desired phase margin, and then we will end up in a frequency. So what are we doing after that? Now, since we know what the frequency is, once this occurs, we have magnitude, phase. This is not going to be k. Here we have some changes. We have a certain omega value. So we need the tau value here. And we will use the 10 degrees here. And omega times tau, basically, omega star times tau is going to be 10. Or less than or equal to 10. So we're going to use 10, and we're basically going to use 10 divided by omega. So omega vec index is going to be tau. Once we have that, we also have basically the gain value here, the magnitude. That's directly going to be magnitude index here. So therefore we have tau, which is going to be tau, and then alpha, again alpha. So once we've done that, I did have this one here. So let's define our transfer function based on this. So it's going to be tf, and then it's going to be tau, and then 1, comma alpha times tau, then 1, and that's going to be it. So now we need to include K2 here, and we actually didn't include K2 here. So basically, this should be times K2, I guess, because that would be then the result that we would read from. The frequency, the phase plot does not change. So this should be basically it then. Now, we have basically flag times gs. So I did combine the p-type controller into flag, so k2. If not, you can just divide this into the p-type controller and then have flag times kp times gs here. So let me just have red and get rid of these. And then maybe this one here. So let's see. I probably did mess up something. We'll see. Or maybe not. Let's see. And we need a little bit more simulation time, like 50 seconds would be the best. And we should pick another color. Let's pick this one here, or maybe green. Let's pick green. So let's have like 60 seconds of simulation time. And then a 60-second of simulation time here. There we go. That's basically it. Now, of course, we can see that we did go a little bit to the left. We have omega 1 now. But the issue seems like we have dropped down the steady state value, probably, like we wanted. It takes even more time here now. So let's call this YSS2 here and see what YSS2 looks like, or even ESS2. ESS2, YSS2. Get also this part here. Let's see. There we go. It's still displaying the old information here. So we can see there's 0.95 and ESS is 0.04. But yeah. We can see that the transients do kind of change for this system. And the reason for that is that it slowly increases like this. So yeah, this is also transient in steady state. When it's finally done, it takes even more time than that. That sometimes happens for these types of systems here. What we can maybe do is to just don't add 10 degrees because we already did add too much to it. So we can have that behavior, which looks a little bit better at this point. And don't worry about the values not being true because I didn't give it enough time to reach steady state. It needs more than 60 seconds at this point. I am a little bit curious about something, by the way, just one thing actually. That being to not adjust it with 42 here. So what happens if I don't add 42 to it? Do we end up in a better solution? Maybe, maybe not. Let's see. So I'm kind of dropping that, not improving on it. I'm just sticking to the actual value. There we go. Let's see. There we go. It's a bit better in my opinion in terms of the solution here. We can see the overshoot is too much, of course, but adding a lag controller gets rid of that and you get a better result here where you can see the transients are even better, but it takes again a little bit time to reach that. It seems like we are forcing it, and this is the best that we can get out of the system because the system is already slow and we try to apply a high gain, even though when we use just a single KP or the P-type controller, this was not even possible because it was not stable. The lag controller was able to stabilize it and force the system eventually to the point where we want it to be, but it seems like our specifications are a little bit off. Maybe not the overshoot here, but to force a system to such a steady state error value is not basically the job of a lag controller. If it is a job of a lag controller, this is the best you can get. Maybe you should opt for a PI controller or PID controller. But here, if you are insisting on using a lag controller, this is the result that you can get. Sometimes pushing and adjusting stuff here is not good, because if this is not your eventual design, if you have still something to add to it, you might leave it as it is here, even though it doesn't satisfy your specifications, and then try to tune it at last. Of course, our overshoot somehow did vanish. The reason behind that is that our system does not overshoot, but it has actually overshoot here, but we cannot see it here. So this is the lag controller part. Now we are going to look at a different system. And the system has delay in it. So run 3.m. So we have basically a system that looks like this. So let's see, what was it? 12 divided by 1, 10, 24. And of course we have delay. I'm directly going to edit. Is it 2 seconds? Yep. So 2 seconds of delay. Now, what is the problem here? Well, calculate the stability interval for delayed system using body graph. Now, this is the point where the body methods shine, because if I'm looking for stability, I'm just going to copy the first two parts here, and we're good to go. It doesn't really matter if we have a system with delay or without delay. It just doesn't really matter. Let's see if it works. While probably these accuracy bounds are not really the best here, we can see that we don't have the precision that we would like to have. Let's have that and that, maybe a better frequency range here. Still didn't cut it. Well, we're off, as you can see. It is just going to 1500 in the phase plot here. So we can just narrow it down a little bit further. Do we have a better view here? A little bit more than that can be useful here. There we go. It hits that margin here. So we can see that our omega vector here seems to be stopping at the value 2, if I'm not mistaken. So at this point, instead of using log space, we can actually go ahead and use lin space here. So let's lin space 0. Maybe 0 up to 2 with 500 points, for example. So maybe 1500. Is that really hard to get? Yeah, we get these stability bounds, but so I guess we don't need this part here, but we'll see. Why are we not seeing? Oh, because it's logarithmic now, we cannot visualize that. Okay, so let's call it 0, 0, 1. It's going to be a little bit off. Yeah, it is going to damage us here. Let me do it like this, but then change the first value here to 1e minus 2. Is that a correct way of doing it? What are the first 4 values here? Yeah, I guess not, but let's see. Yeah, this doesn't help. Let's also drop lint space and start from 0.01 with 0.0 steps up to 2. That makes more sense, I guess. Because with lint space, we're generating awkward vectors. And this doesn't seem to cut it for some reason. Interesting. Let's have 1.54 maybe. It is bothering me because the values here are a little bit off. I want to increase the accuracy as much as possible, but it seems like it's not that easy. So let's hit it better. Not that. Oh, yeah. Let's reboot MATLAB. The problem is that here, I'm going to explain it in a minute, why we have such issues when defining an omega vector here. But the issue comes from the fact that this is a delayed system, and the delay part affects basically the phase plot here. So to hit the exact value with high precision is quite interesting because it's not really that possible if you are not doing it symbolically. So numerically hitting that is hard. So we will be okay with maybe 1 here. It should, interesting. It does hit the upper bound, but doesn't hit the lower bound, I guess. Still not, what is this value that we're 0.0 off. Oh no, wait a second. It's the negative part that we're missing, yeah. Well, this should work now, okay. Nice. Are we displaying it on here? There we go. Now we can see that you can see that the magnitude values drop down quite a bit. The stability boundary is within a certain limit, and the reason behind that is the following. We have basically this equation here, but now we also have x to the power of minus 2s or 2j omega. Now, let's add this portion to here too. And you can see that when we're calculating basically the p-type controller, what we can do is we can just do it like this. And the magnitude of e to the power of minus 2j omega is basically 1. It's the phasor representation itself. So it has basically gain 1. Therefore, it has an effect on the argument. And we're going to add to the argument of this here. And the argument of e to the power of minus 2j is minus 2 omega. Minus 2 times omega. But of course, be careful because this 2 omega is actually in radians. So what you have to do is you have to multiply with 180 and divide into pi. So this times 2, so 2 times this here, gives us 114.59. So let me just rewrite this. Times omega. So this is nothing to neglect. This is an issue because if omega increases, we directly tend to infinity. If omega tends to infinity, this whole argument stuff tends to infinity. And There's an interesting fact that if we, for example, put in 1 in here, then the system has also a certain contribution. We might be already off the stability boundary. So this has a negative effect of on the phase plot. So it kind of uh, explains the reason why we tend to J infinity, negative J infinity here in the phase plot. And it is harder to hit this with a certain precision. We're searching for the phase value, for example, 180 degrees. And if you're using logarithmic scaling, it's quite almost impossible to hit the target there. So if you're dealing with MATLAB and systems with delay, you might look for linear spacing even, because it might not exceed 1 radians or 10 radians for, as it is the case for this system. Of course, there's no general rule. You should look at the system, the body plot of the system, and see what frequency range is the best here. And we can see that we have basically these 2 points. The interesting fact is that I just adjusted omega vec and I didn't think about anything else. I can just use the same algorithm, the same approach. I'm looking for minus 180 degrees. And once that's satisfied on the phase plot, I get the frequency, plug it into the um, magnitude, take the inverse, and that's the k value that I'm interested in. And the same goes for this one here. So what we might do here is we might plot on AX2, t comma y, maybe just one plot maybe to show you that that's the case. So y comma t, step, gs, actual feedback, gs, comma 1, and the k value, which seems to be 2.15, so maybe 2 times gs is in the stability interval. So there we go. You can see the value 2 has high oscillations, and if I'm going to increase it, this will become unstable as soon as possible. Another note for classical exams, we know that the body plot is not affected by the magnitude plot of this is not affected by the delay part here. So sometimes it's quite possible that in the exams you get a body plot of the minimum phase part, 12, 1, 10, 24, without the delay effect, and then you're asked to take that into consideration. What you have to do is you have to write the equation like this and try a certain omega value, look at the body plot, what the angle here is, and try to come up with the exact value. You have to iterate a little bit, like plug in omega 0.01 or 0.1, look at the argument of the system. You will see that it doesn't hit 180. If it's less, increase omega. If it's higher, decrease omega, and kind of try to find the actual value of omega that you're interested in. And then once you have acquired the omega value, then it's quite easy. You will look at the um, gain plot, and then you're good to go. It is possible to use this method in conjunction with everything that we've talked in run 1 or the first portion of this today's lesson. It is possible to combine them. For example, you might get a body plot of this portion here, and you might be asked to add a delay part and then try to come up with a p-type controller that has 10% overshoot, and on top of that, maybe you're designing a phase lag controller to get a better steady state behavior out of it. So if you are studying for an exam, maybe you should try to do that when still you have still MATLAB available to you now. So you can try it on paper, try to do it with a pen and paper, and then validate it in MATLAB. So I would highly suggest you or recommend you to do that exercise on your own. So there's also the lead controller design and other designs on using the body plot and the frequency domain. But the heart or the core part of the frequency domain is that we have basically this relation here. We're looking for a 1 divided by 0, so a division by 0. That brings us to this point here. You should be uh, you should be considering this equation here, or this equation for the negative one, so that if you have a dynamic part, we're looking for basically F times G. Everything on the loop here is basically in here. So let me give you the generalized version of this. Instead of having K, your generalized equation for a certain controller and system for this connection. So let's get rid of that. So this is basically F omega times G omega, F omega times G omega. So we have this connection here. So if this is the setup, and if you're trying to use the body plot, it means that you're basically checking this point. If it is stability, then it looks like this. If it is a synthesis problem, then you also need to maybe use, where is it? Let's just take this part here. If it's a synthesis problem, you might want to take, you might want to look for overshoot, for zeta, for a phi m. So like this, for lag controller, the 10 does not come with the without the lag controller. You should basically consider these two here, or maybe also the A10 version. If you're given the A10 version, use that one. So or this one here, doesn't matter. Then you're looking at plus phi m. So that's basically it. For synthesis, you're going to set it to a lower value than or a safer value than minus 180 degrees, because this is the stability bound. You should be on the left of the stability bound somewhere. And if this is a p-type controller, you can just plug in K and then work your way out. If this is a lag controller, you have seen that we have basically approximated this. We have plugged in K, bring it out, but then the other part has no gain in it, so alpha and tau is used in order to eliminate the DC gain of the lag controller, but it has effect here. If it's less than or equal to 10, you can add 10, then it will subtract 10, it will correspond to the same stuff. Then you can go ahead and read the value from here, use that frequency and the gain value to come up with the lag controller. You know how to handle the p-type controller. For the lead controller, it will be beta instead of alpha, and there are some other assumptions, but it is quite similar. You can use your lecture notes to study that part. If your system has lag in it or delay in it, you if you have MATLAB, or if you can generate the body plot as you wish, you might go ahead and do that. If not, you might have to adjust your body plot. Maybe just change the values of the y-axis of your gain plot or phase plot accordingly, or you might end up in a point where you have to use this kind of approach to guess the omega value as exact as possible. So that's basically it. There are much more things that we can talk about the body plot, but the best way is to try to design each controller that is available to you, and the homework was actually designed for this, so you get a better view of this. In the PDF you can see there are explanations, some code parts. The numerical parts may differ because I choose parts, but it seems like I did go with the actual part here. I did also add the phase lag controller here, and you can see that there's a negative effect. It drops down this part here, so it amplifies the gain. That is kind of obvious then there. And there's this lag part. You can also see that the gain plot with delay and without delay is basically the same, but the phase part here is quite different when you add delay to it. So when you add delay to a system, you can also assume that you will hit the stability bound much earlier. Therefore, your stability interval will drop down because you have a certain gain value here. And if you hit it earlier, you will hit the stability bound, or the stability bound will be a smaller interval. So that's basically it for today. I hope that this was helpful. This is basically frequency domain, week 10. So the next week will be then about state space, and then we will basically conclude our laboratory sessions for this lesson. So see you in the next video.